Hello, everybody, and welcome to Scalar's YouTube channel. This is Mahima Hans, and I'm a software engineer and a tech placement mentor. So, this is Sorting Algorithms Part 2, and today we're going to be covering selection sort and merge sort. So, before we get on with the video, make sure to check out Scalar's free masterclasses by industry leading experts on Scalar's event page. Link is in the description. So, without further ado, let's get started with the video. So now let's move on to selection sort algorithm. So as the name suggests, this algorithm repeatedly selects the smallest element and it puts it at the right position. So in bubble sort, we were repeatedly swapping the adjacent elements and moving the largest element to its correct position first. But here we'll just pick up the smallest element out of the array and we'll put it at its correct position. So we will start iterating over this array. We'll find our smallest element to be 1. And for the smallest element, the correct position should be the 0th index. So we'll just swap it with the element on the 0th index. So our array will become 1, 9, 4, 5, 2. In this case, the array till here is sorted. So we don't have to bother anymore about the array till the 0th element. We'll start from here again. We'll pick out the smallest element from this portion, from the unsorted portion, and then we'll swap it with this element here because this is the correct position for the smallest element in this part of the array. So now we will just swap 2 with 9 and it will become 1, 2, 4, 5, 9. So this much part of the array is sorted here. From this part, we'll again go. We'll pick up the smallest element, which is 4. And it's already at its correct position. So let's move on to the next iteration. So now the array till 1, 2, 4 is sorted. We'll go over 5 and 9. We pick up the smallest element, which is 5. It's already sorted. So that's also done. So we'll say 1, 2, 4, 5, 9. So now we reach a stage where 4 out of the 5 elements have been put in their right position. That's how we did in bubble sort as well, that when n minus 1 of the n elements are sorted, the last element is already in the correct position, right? So here our selection sort will also end. So we will have n minus 1 iterations here also. Let's quickly write what we reduced from this iterations and then we will move on to the pseudocode for this algorithm. So basically, we are iterating n minus 1 times because we have to pick the n minus 1 smallest elements and we have to put them in the right position. And the last element will already be sorted after that. And for n minus 1 times, we have to pick up the minimum and swap it with the right index it has to be at. So what we observe here is that in the first iteration, we were going through all the n elements and we were picking up the smallest from those. So we were starting from the 0th element going till n minus 1th element. In the second iteration, since this part till the 0th element was sorted, we were starting from the first element and going till n minus 1th element. Again, in the third iteration, we were starting from the element at index 2. We were going till n minus 1. In the next one, we'll start from 3 and so on. So basically, we will have n minus 1 iterations to pick up the smallest n minus 1 elements, put them in the right position. So I will start from 1. It will go till n minus 1 for the n minus 1 iterations. And then we will start picking up elements from the I minus 1th position. So in the first iteration, we were starting from 0, right? In the iteration I equal to 1. So we'll start from j equal to I minus 1 and we'll always go till the last element. So j will be less than equal to n minus 1, j plus plus. We will try to find minimum element when we are in this loop. We'll try to find the index at which the minimum element is present and then we will do the swapping. I will show this part in the code itself. But the basic idea is to start from the I minus 1th element in the ith iteration. In the first iteration, we started from the 0th element. In the second, we started with the first element. The third, we started with the second element and so on. So now let's get to the code for selection sort algorithm. So as we did in our pseudo code, we will have n minus 1 iterations. Start right from 1, go till n minus 1. And in every iteration, we'll start our j from I minus 1. Right? We'll start comparing from the I minus, we'll start picking up the smallest element from I minus 1th index, and we will go till the last element of the array, which is at the index n minus 1, do a j plus plus. Now for every iteration, we have to find the minimum element, right? So let's just assume here that the minimum element is present at the I minus 1th index. We're starting from I minus 1. I'm just assuming that the minimum element is present at this index only. We will, however, now find out where exactly the minimum element is present. So we'll just check if element at position j is less than element at position mini. We'll update our mini variable. So our mini will become j. Now when we have iterated through the complete unsorted part and we have found out what index our minimum element is present at, we'll simply swap our element present at the minimum index with the element present at I minus 1. So initially, we will be setting the element at the 0th index. When we're in the first iteration, we'll be setting our first minimum element, which is the smallest element in the array, on the 0th position. In the second iteration, we'll be setting it at the first position, which will be the second minimum element, and the third minimum element on the second position, and so on. So this should do. And let's just test our code. Let's take the example. The one we were considering, 91452. The length remains 5. Instead of bubble sort, let's quickly call selection sort algorithm. Let's run our code. Yeah, and it gives our elements in the sorted order. So that's how selection sort algorithm works. Let's quickly go over the time complexity of this solution as well. So as we observe here, for the first time, we are going from 0 to n minus 1. So we are iterating through n elements. The second time, we are iterating to n minus 1 elements, then n minus 2 elements, and so on. So this also boils down to the same formula that we were looking at earlier, which is the sum of first n natural numbers. So this becomes O of n into n plus 1 by 2, which is similar to O of n square. And our space complexity will be O of 1, since we are not using any auxiliary space while running the solution. So now let's look at some advantages of selection sort and some disadvantages. It is easy to understand. It's a simple algorithm and it works well with smaller data sets. However, if we move to the disadvantages, it is a time complexity of O of n square again, which is inefficient for larger data sets. Plus, it does not preserve the relative order of the elements. So, we were seeing in bubble sort that the relative order of the elements was getting preserved when we were swapping, and it was a stable algorithm. But here, if you see, we're just picking up the smaller element and we are swapping it. So, the relative order does not necessarily have to be maintained here. So, when we were, say for example, when we were picking out 2 here and we move 9 to the end. So, the relative order of 9, 4, 5 got changed and it is not the same. So, selection sort is not a stable algorithm. This is one of the disadvantages of selection sort algorithm. So, let's talk about merge sort first. So, merge sort is an algorithm which uses a technique called divide and conquer. So, what we do in divide and conquer is that we basically divide the problem into smaller sub-problems. We solve those sub-problems first and then use their solution to solve our bigger problem. So in this case, our problem is related to arrays, right? So we'll be dividing our array into smaller sub-arrays. We'll be sorting each sub-array and then we'll be merging the sorted sub-arrays back together to form the final sorted array. Let's take an example and try to see how it works. So let's say our array is consisting of 8 elements and we have 6, then 2, then 8, 4, 9, 1, 16, and 3. Now we'll be dividing it into sub-arrays. So let's say our sub-arrays are 6, 2, 8, 4. So we're just partitioning it at the middle and we are getting 2 sub-arrays. 9, 1, 16, 3. Now we'll be, so essentially what we want is we want to solve these 2 sub-arrays, we want to sort them out and then we want to merge them to find the solution of this one. But this is a recursive algorithm. So merge sort and quicksort are both recursive algorithms, and if you are someone who's a beginner in recursion, I would recommend first please go through the basic concepts of recursion and then circle back and watch the remainder of the video. So as I was saying, we'll divide the array into sub-problems and now we'll solve these sub-problems. But now to solve these, we need to further divide it to a point where we can't divide it any further. So let's see, we'll divide these as well. We get 6, 2. Here we get 8, 4. Here we get 9, 1. We get 16, 3. Now we divide these further as well because there are 2 elements in these sub-arrays. And we get to a point where we have 1 element in each sub-array. From this point, we can't divide it any further. So we return from our recursion and we'll start merging these sub-arrays. And we'll merge them in a manner where each of these sub-arrays, where for each of these sub-arrays that we merge together, the result will be sorted. So let's just quickly partition them. Now I'll start merging. So now I have 2 and 6. So if I'm merging them in sorted order, I will have 2 and then 6. For this one, I will have 4 and then 8. This one, I will have 1 and then 9. This one, I will have 3 and then 16. Now I'll merge these two together. I will have 2, 4, 6, 8. We will talk about the exact details on how to write efficient code of merging them together. But just bear with me for some time and try to understand how the basic flow is working. Sure, we'll have 1, 3, 9, 16. And once we merge these two together, we will have our final array, which will be 1, 2, 3, 4, 6, 8, 9, and 16. So that's how merge sort works. Basically, it divides it into sub-problems. The base case here is when we're left with 1 element or 0 element. So if we reach a point where we can't divide it further, right? That is here, where there's just 1 element left. That's our base case. After that, we start merging it and we start returning the sorted sub-arrays, and at the end, we merge it to get our final solution. So let's discuss now how this dividing and merging is happening. So let's say we have an array of length 6. We're trying to divide it into equal halves. So for length 6, we'll be dividing into 2 equal halves of length 3. Now that we stumble upon arrays of odd length, what we can do is we can keep 2 elements in one sub-array. I mean, half, like if you can divide it by 2 and add an extra element in one of the sub-arrays. So 2 elements in one, 1 in the other. Similarly for this array. And now for these, we'll just divide it into 2 arrays of 1 element each. So in code, how we're going to do it is, let's say this is our left index. This is I equal to 0. This is called as left. And this is I equal to n minus 1, or let's say I equal to 5 here. So this is right index. So we'll calculate our mid. So mid will be L plus R by 2. That will give us the middle index for this array. So it will be 0 plus 5 by 2, which will give us 2. So this is our mid, this 8 index. The index whose value is 8. So to divide, we'll just divide our array into two subarrays. The first will go from L to M, and the second will go from M plus 1, and it will be till R. Now, our for this subarray, we get L as 0, and this M, which is actually the right index for this subarray, this comes out to be 2. So to divide this further, we'll be doing 0 plus 2 upon 2, which will be equal to 1. So 0 to 1 will be one subarray, and 2 to 2, which is M plus 1 to R. So 2 to 2 will be this one. So uh, this is an array of length 1. So this way we can divide, basically calculating the middle and then dividing it based on L to M in one subarray and M plus 1 to R in another subarray. So we'll keep dividing this until and unless we land at a place where we are left with just one element. Now we'll understand how we are merging two sorted subarrays together. So after we divide them into subarrays, the next task is merging them in a way that the result comes out to be sorted at each level of merging, and eventually our final answer contains the whole array as sorted. So let's take the same example and we will try to merge it. So let's start merging these subarrays together. So first we'll merge these parts. It's easy to merge them, so I'm just writing it. I'll illustrate on exactly how it's done in the coming examples. So this will also be merged very easily. Now let's merge these two parts. One is 3, 6 and one is 8. So we'll have two pointers, one at the beginning of this subarray and one at the beginning of this subarray. So now, since all of these are sorted, so the smallest element of the first subarray is at the first place in this, and the smallest in the second is at the first place in that one. So whatever is the smaller of these will be the first one in the merged subarray. So 3 is smaller out of 3 and 8. So 3 comes first. We move our pointer further. Now the smallest pending element will be calculated out of this pointer and this pointer. Now 6 is smaller, so 6 comes first. We move further, this array is finished. Now comes 8. Similarly, in this one, we have two pointers, one on 2 and one on 9. Since 2 is smaller, 2 comes first. Now the pointer moves here. We have to calculate the smaller from all the pending elements in this array and this array. So since this one is smaller, we'll consider this one first and move our pointer. This is ended, so we take 9 from this subarray. Now let's solve our larger problem. So merging these two subarrays will give us the final answer of our array, like the sorting of our question. So as I did earlier, we will have two pointers. Both are sorted, so whichever is smaller will come first. So 2 will be the smallest element and it will move further. So out of 3 and 5, 3 is the smaller element, so we'll put 3 here and we'll move the pointer further. Now we'll consider 5 and 6, and since 5 is the smaller one, we'll take 5 in our output and move the pointer for this subarray further. So now we have 6 and 9 in comparison, and since 6 is the smaller one, we consider this in our output and move the pointer further. Now we have 8 and 9. We'll take 8 in the output since it's the smaller one and move the pointer further where this subarray is finished. Now we'll take 9 since it's the only element left. If we had another element here, say 10, we would continue in this subarray. So whenever any one of the subarrays is finished, we'll take all the elements remaining in the other subarray so that we can take all the elements in our output. So that's how merging the sorted subparts will work. Now let's discuss the pseudo code for our algorithm. So if we see on a high level, what we did was we divided our main array into two sub-arrays. Then this part of work includes sorting these subarrays. We're doing it recursively, yes. We're dividing it further into smaller subarrays, merging them. So yeah, this consists of dividing it into a lot of subproblems. But the basic thing that we're doing is dividing an array into two subarrays, sorting them out, and then merging them. So that's how our pseudocode or logic for our recursion will be. So let's quickly write the pseudocode for it. So we'll just have merge sort. We'll have an array. We'll have a left index. We'll have a right index. We'll be calculating the mid index as I discussed. It will be L plus R by 2. We'll have, we'll be then focusing on sorting the two halves. So the first part will be from left to mid. So we'll call merge sort recursively on array, and our starting point will be left, ending point will be mid. Then we'll be calling merge sort on the right part, which will be array, mid plus 1, and right. And now we'll merge the divided parts together. So after sorting them, we'll write a merge function for that. And this will take our array, this will take our left, mid, and right. So our base case for this recursive function would be if L is greater than equal to R. So this essentially highlights the case when we are left with just one element. So in that case, we'll simply return because we don't need to do any processing on that part whenever we have one element left. So we'll simply return and start merging from there. So that's the pseudocode for the merge sort recursive function. So now let's jump to the coding part. So I'll create a function merge sort. This will take my array. It will take the left index as we discussed, and it will take my right index. So let's quickly write our base case, which is if L is greater than equal to R, we'll simply return. So now we'll be dividing the array into two parts. So we'll calculate our middle index, which is L plus R by 2. So now we will recursively sort these subarrays. So we'll call merge sort on the first half, that is L to mid. And we'll call the merge sort on the second half. We'll sort it out. That will be mid plus 1 to R. And then we'll merge these arrays. The merge function will accept the array. It will take left, it will take right, and it will take mid. So now let's implement the merge function. Before that, let's first understand how we are going to be writing the code for the merge function. So for the merging part, let's say we have this array where we're already done dividing and sorting the subparts. So we have this part 2 to index 0 to 3, which is already sorted, and we have the other part 4 to 7, which is already sorted too. So now we have to merge both of them. So this is our left index, this is middle, and this is right. So how we'll go about it is we'll have a pointer here, let's call it I1, and we'll have a pointer here, let's call it I2. One at L and one at mid plus 1. So we'll see, like we were talking about merging earlier. So we'll see which one of them is smaller and keep it in the output. So our output will be currently an auxiliary array. Let's take an auxiliary array, an auxiliary space of length 8. So whatever one is small, we'll put that one in the auxiliary array. So out of 2 and 1, we'll be putting 1 here. And we'll be progressing I2 to the next index. So out of 2 and 3, 2 is smaller, we'll put 2 here. We'll be progressing I1 to the next index. Out of 4 and 3, 3 is smaller, I'll put 3 here. I2 comes here. Now out of 4 and 9, I'll move I1. Then out of 6 and 9, I'll move I1 again. So after 6, I will have 8 and 9. So I'll move I1 again. So here I1 will be allowed to move till M only. So as soon as we encounter this, we'll stop iterating on the first subpart. So we'll put 8 here. And now all we have is the second subpart. So we'll put all the remaining elements of the second subpart in our output subarray. So we'll put 9 and 16 here. So this is how our merged output, which is like consisting of sorted subparts, but now after we merge them, the whole array is merged. So this is in an auxiliary space right now. What we'll do after this is just replace the elements in the original array with this final output array. So from L to R index in the original array, we'll just basically put all these elements that we've calculated in the output auxiliary array. So let's write the code for the same. So we'll have a function void merge. It will take our array. It will take the left index. It will take the right index and the middle index. So as I said, we'll be creating an auxiliary array first. So let's just call this auxiliary array as merged. And the size of this array will be r minus l plus 1. So in our previous, so basically it's got to be the same size as the number of elements between l and r inclusive. So in the last example, our l was 0 and our r was 7. So the number of elements is 7 minus 0 plus 1. So the difference plus 1 for including the l and r. So we'll take a merged array of size r minus l plus 1. We'll have our I1 at L. We'll have our I2 at mid plus 1. So, yeah. So now we'll have a while loop where we'll have our I1 starting from L and our I2 starting from mid plus 1. We'll check whatever pointer is small. We'll progress that pointer and add that element to the merged array. So let's write a while loop while I1 is less than equal to mid, because our first subarray is only till the mid index and our I2 can go till R. So now we'll be comparing elements at index I1 and I2. So for whatever subpart the current element will be smaller, we'll be adding that as a part of our merged array. So we'll be checking if element at index I1 is less than equal to element at index I2. We'll be considering this element, so we'll be adding it to merged. Before that, let's maintain an index for the merged array. So it will start from 0, and as and when we add an element, it will keep incrementing. So firstly, our I1 and I2 will be at L and mid plus 1, and the auxiliary array will be of length R minus L plus 1. So this merged array will start from 0 and it will go till R minus L index. So we'll just keep incrementing it as and when one of I2 or I1 is increased and one element is added in the merged array. So it initially starts from 0, and now we'll just say merged I equal to array at index I1 because that was smaller. In the other case, we'll just populate merged I with array I2. And if we are populating with I1, we'll say I1 plus plus, we'll increment that pointer, otherwise we'll be incrementing I2 pointer. Also, I will be incremented every time we add an element. So now considering the case where one of the array gets exhausted, so either the first part is all done, all the elements are added, but the second part is left, or the second part is over and the first part is left. So for both of these cases, we'll write separate for loops. So while I1 is less than equal to mid, we'll just say merged of I equal to array of I1. And we'll do I plus plus, I1 plus plus. Similarly, we'll write for the second subpart. If any element in that subpart is pending, we'll just say while I2 is less than equal to R, we'll put merged I equal to array of I2. We'll do an I2 plus plus and I plus plus. So that sums up the code for the merge algorithm as well. Now just write our example and try to run merge sort on an array. So we'll call merge sort. Let's consider this array first, and we can check out other examples later. So it expects an array, it expects left and it expects right. So initially when we are calling it from the main function, the left should be 0 and the right should be n minus 1, which is 7 in this case. Cool. Let's see and run. This is just a small spelling error. Let's run it again. So let's quickly get rid of this error. Also, guys, we forgot one thing. So after we populated the merged array, we had to copy the contents of the merged array and add it at index L to R in our original array. So I'll write the code for that here. So we'll start with 0 index for the merged array. We'll start with L index of the original array. We will have j less than equal to R. We'll have I plus plus, j plus plus. And we'll just simply say array of j is equal to merged of I. So that should populate our original array with the sorted elements. Now let's run our code. Yeah, so that works well and it sorts out our elements. So yeah. So now let's talk about the time and space complexity of our merge sort algorithm. So what we are doing essentially is we are breaking down our array into 2 subparts at every step. Then we are further breaking down these subparts into 2 subparts again. And this continues until we are left with a part where the number of elements in the part is only 1. So the time complexity for that will be O of log n. And when we are merging at every step, the number of so we're going to be iterating over n elements. So for that, the time complexity will be O of n every time. So our time complexity for the merge sort algorithm boils down to O of n log n. And this is the best case, worst case, and average case time complexity for our merge sort algorithm. Now, talking about the space complexity, since for merging we are creating an auxiliary space and the size of that space can be maximum n, so the space complexity for our merge sort algorithm is O of n. So that's it for today, guys. In our upcoming videos, we'll be covering quick sort and the searching algorithms. If there are any other topics that you'd like us to cover, make sure to mention them in the comment section. Also, do like and share this video and make sure to subscribe to Scalar's YouTube channel for more such insightful content. See you!